In this video, we'll talk about the intermediate field Zeeman effect. We'll start by reviewing the strong and weak field effects. Then we'll calculate the intermediate field Zeeman effect for n equals 2, computing the W matrix, which is an 8 by 8 matrix, and then applying the block solutions to get the final energy eigenvalues. So in a weak field, the Zeeman effect is just a perturbation on the spin-orbit coupled states. And so the good quantum numbers are n, l, s, j, and m sub j, where the total energy, E, is equal to the Bohr energy plus the fine structure energy plus the perturbation that comes from the Zeeman effect, the weak field Zeeman effect. We can write this energy as minus E1 over n squared times the quantity 1 plus alpha squared over n squared, where alpha is the fine structure constant, times the quantity n over j plus a half minus 3/4, and then you add in the Zeeman correction, E sub z1. E1, of course, is 13.6 electron volts. E sub z is given by, in this weak field effect, mu sub b times the B external times m sub j, this is the Bohr magneton, of course, times the quantity in the brackets, which is 1 plus j times j plus 1 minus l times l plus 1 plus s times s plus 1 over 2j times j plus 1. In a strong field, the fine structure interaction is the perturbation, and the standard hydrogen atom states, which are eigenstates of the Zeeman effect, are the ones that are being used. In this case, n, l, m sub l, s, and m sub s are the good quantum numbers, and the total energy is given by minus E1 over n squared plus mu sub b, B external, times the quantity m sub l plus 2m sub s, and then you add in the perturbative term from the fine structure, E sub fs1, where E sub fs1 is given by E1 over n cubed times the fine structure squared times the quantity 3 over 4n minus the quantity L times L plus 1 minus m sub L m sub s over L times L plus a half times L plus 1. And this is valuable for L is greater than 0. For L equals 1, it's a slightly different quantity. Now, if we look at what these two effects do in terms of splitting the n equals 3 level, we can see that in the weak field Zeeman effect over here, first we have a highly degenerate level where n equals 3 has lots of states in it. There's 1, 2, 3, 4, 5 up here, then there's another 8 here, and then there's another 4 here. So, when you apply the fine structure and change the spin-orbit coupled states, you get a splitting of the degeneracy so that now you have 2j equals 1/2 states down here, you have 2j equals 3/2 states here, and 1j equals 5/2 state here. When you then apply the weak Zeeman effect, each of these states with j equals 5/2, 3/2, and 1/2 will split according to the m sub j. And so you have m sub j minus a half plus a half for these two sets, and then the same thing with the minus 3/2 all the way to plus 3/2, and then minus 5/2 to plus 5/2. So if you count the number of states for n equals 3, you get 1, 2, 3, 4, 5, 6 states up here. Then you have another 8 here, that's 14, and then you have another 4 here, and that's 18. On the other hand, if you have a strong Zeeman effect, you start with the highly degenerate n equals 3 state. You split that out into 7 states where m sub l plus 2m sub s is different. So you have 7 states with m sub l plus 2m sub s, in this case going from plus 3 all the way to minus 3. When you then apply the fine structure, you then split these out further so that the m sub l plus 2m sub s state just is 1, and so it stays as 1, and the plus 3 is 1. But the one with m sub l plus 2m sub s splits its degeneracy into 2. The one with the plus 1 state has 4. The 0 state has 4. The -1 state has 4, and the -2 state has 2. These are going to also be 18 states, but they're split in different ways because you first apply the Zeeman effect being strong and the fine structure effect being weak. So what about the intermediate field Zeeman effect? This is the case where you can't say that one, either the Zeeman or the fine structure is stronger. So if you assume that they're approximately equal, then you must apply degenerate perturbation theory, with the total Hamiltonian, perturbative Hamiltonian, being the sum of the Zeeman and the fine structure terms. So let's consider the n equals 2 case, that is L equals 0 and L equals 1. We'll start with the LS coupled basis stat with quantum numbers L, S, J, and M sub J, instead of the L, M sub L, S, M sub S states. Now, I could do the opposite and start with these, and I would get the same answer eventually. But we're going to start with this particular set here. In that case, for L equals 0, there's only one value of J, which is equal to 1/2. And there are two possible values of M sub J plus or minus 1/2, which are directly related to the value of M sub S. So what I'm interested in doing is taking this state that is in L, S, J, and M sub J and breaking it up into the states with good quantum numbers L, M sub L, S, and M sub S. And I can write that down very simply. So for L equals 0, we have psi 1 is equal to, we call psi 1 as the state 1/2, 1/2, which is J, M sub J, and that's equivalent to the product state L equals 0, M sub L equals 0, S equals 1/2, M sub S equals 1/2. There's a direct congruence between these two states. Psi 2 is a 1/2 minus 1/2 state, again with L equals 0, and this is now the L equals 0, M sub L equals 0, S equals 1/2, M sub S equals minus 1/2. Now, why am I enumerating both of these? Because in the case of the Zeeman effect, I need to know what the individual values of M sub L and M sub S are to calculate the Zeeman energy correction. Whereas with the fine structure, I need to know J and M sub J. For L equals 1, there are more mixing possibilities, since M sub L is -1, 0, and +1. So what we're going to do is use the 1 by 1/2 Clebsch-Gordan table to generate all the possible states of J, M sub J, and break them into states, product states of M sub L and M sub S. I've listed here the Clebsch-Gordan table entry for 1 by 1/2, and we'll start by picking out all the possible combinations to build the remaining degenerate states. The first one, for L equals 1, these are all for L equals 1, we'll call psi 3, which is a 3/2, 3/2 state, which is up here. Now clearly this only has one possibility, and that's going to be a 1/1 for L, M sub L, and a 1/2, 1/2 for L, S, M sub S. Similarly, down at the bottom here, the 3/2 minus 3/2 is going to be a 1 minus 1 and a 1/2 minus 1/2. The next state we'll look at, psi 5, is the 3/2, 1/2 state, which clearly has two different contributions, one from this and one from this. And we can write that down as square root of 2/3 times the state L equals 1, M sub L equals 0, and S equals 1/2, M sub S equals 1/2. Plus the square root of 1/3 times the state L equals 1, M sub L equals 1, and S equals 1/2, M sub L, S equals minus 1/2. Now I'm going to include this one because the product includes both the same states. The 1/2, 1/2 state, we're going to call that psi 6. And that is square root of 1/3 minus square root of 1/3 times the 1/0 state times the 1/2, 1/2 state, plus square root of 2/3 times the 1/1 and 1/2 minus 1/2 states. I then move down to this block here, and I have the 3/2 minus 1/2, which is state 7. And that has two contributions, again, the square root of 1/3 times the 1 minus 1 state and the 1/2 state, plus square root of 2/3 times the 1 0 state and the 1/2 minus 1/2 state. And finally, psi 8 is the 1/2 minus 1/2 that has the same two states combined in the m sub s, m sub l basis, but with different coefficients. So we have minus square root of 2/3, 1 minus 1, 1/2, 1/2, plus 1 square root of 1/3, 1 0, 1/2 minus 1/2. Now I've listed these in a very specific way, as you'll see in a minute when we go through the whole block. So we have then 8 different functions, psi 1 to psi 8, for n equals 2 and L equals 0 and 1. And these are all degenerate, with quantum numbers L, S, J, and M sub J. And we can list them as follows. So these are exactly the same 8 states that I listed before. And you can see that the first 4 are unique states, and the next 4 are mixtures of 2 states with M sub L and M sub S. These 2 are the same 2 states. These 2 are the same 2 states. Now we're going to build the W matrix for the perturbation matrix H prime, which is H prime sub Z and H prime sub Fs. So I'm not actually going to do those calculations. You can do them in problem 729. So we'll write them down instead. But in order to do this with a shorthand, we're going to define 2 terms. Gamma is related to the fine structure coefficients, and it's just the fine structure over 8 squared times 13.6 eV. And beta is related to the Zeeman effect, and it's going to be equal to the Bohr magneton times the external magnetic field. So now I can write down this W matrix. It has a minus sign in front, and then it has diagonal elements. And we start with the diagonal elements for psi 1. So this is W11, which is 5 gamma minus beta. Now remember, we're in the basis set of J and M sub J. And if you recall, that diagonalizes the fine structure constant, the fine structure interaction. It does not diagonalize the Zeeman interaction. So we'll see what the consequences are of that in a minute. Then we have the W22, which is 5 gamma plus beta, the W33, which is gamma minus 2 beta, and the W44, which is gamma plus 2 beta. We then have the gamma 55, which has W55, which is gamma minus 2/3 beta. Then we have 5 gamma minus 1/3 beta, gamma plus 2/3 beta, and as you might expect, 5 gamma plus 1/3 beta. Now, we also have some off-diagonal elements. And as you might expect, because we're using the basis set with J and M sub J, these will not include anything that belongs to the fine structure, because the fine structure is diagonalized. However, they will include terms that include beta for the Zeeman effect. And in fact, we have the following. We have square root of 2/3 beta and square root of 2/3 beta that are a mixing between psi 5 and psi 6. And then we have the same terms, which are mixing terms between psi 7 and psi 8. Again, square root of 2/3 beta and square root of 2/3 beta. Everything else is 0. And so, as we expected, because we're using the basis set that diagonalizes the fine structure, all the gammas appear on the diagonal only, and all the betas appear not only on the diagonal, but there are some off-diagonal terms. But this is a very sparse matrix. Most of these are 0, and we notice that the first 4 terms do not interact with any other functions. And so those first 4 terms, psi 1, psi 2, psi 3, and psi 4, are already eigenfunctions of the full perturbation, because they have no interacting matrix elements with any of the other functions. The other 4 eigenfunctions, this red block and this blue block, are just easily solved by a 2x2 block. And then you put a minus sign in front to get the final value. So we can solve for the energy by solving 2 2x2 matrices. Now let me point out one more thing. If I had chosen, as I said at the beginning, to do this with the basis set that was the M sub L and M sub S basis set, that is the hydrogen atom basis set without the spin orbit coupling, then the Zeeman effect terms would all be diagonal only, and you would only see betas along the diagonal. And the off-diagonal terms would belong to the fine structure. So you would have some off-diagonal terms for the fine structure because that is diagonalized only in the spin orbit basis set. So now we can solve the two blocks. The first block you solve by diagonalizing the 2x2 submatrix that looks like this. So that was the one in red. And we can do that the usual way by setting the determinant of this matrix minus the identity matrix times lambda to 0. So when we multiply this out, we get 0 is equal to gamma minus 2/3 beta minus lambda times the quantity 5 gamma minus 1/3 beta minus lambda minus 2/9 beta squared. I can now multiply this all out. I get lambda squared plus 5 gamma squared plus 2/9 beta squared minus 11/3 beta gamma minus 6 gamma lambda plus beta lambda minus 2/9 beta squared. And clearly this term and this term will cancel. That leaves us with 0 is equal to lambda squared minus lambda times 6 gamma minus beta plus the quantity 5 gamma squared minus 11/3 beta gamma. I can solve this using quadratic equation and realizing that the solution is negative because the W matrix had that minus sign in front. I can write that minus lambda plus minus is equal to the solution of this quadratic equation, which is 3 gamma minus beta over 2 plus or minus 1/2 times the square root of 36 gamma squared minus 112 beta gamma rather, plus beta squared minus 20 gamma squared plus 44/3 beta gamma. Now you add these together, these two terms, they give you 16 gamma squared, and then you can add these two terms together as well. And this is, when you multiply that times 3 is 36 thirds. And so 36 thirds subtracted from 44 thirds is 8 thirds. We can then factor out a factor of 4, and we get the final solution for lambda plus minus, which is equal to minus 3 gamma plus beta over 2 plus or minus the square root of 4 gamma squared plus 2/3 gamma beta plus 1/4 beta squared. You can solve the second block in exactly the same way. It has slightly different values on the diagonal. And so when we do that, we have the initial expansion here. We expand this out. Again, these two terms, the 2/9 beta squared, will cancel. We're now left with 0 is equal to lambda squared minus lambda times 6 gamma plus beta plus the quantity 5 gamma squared plus 11/3 gamma beta. We again use the quadratic solution, and we get lambda plus minus is equal to minus 3 gamma minus beta over 2 plus or minus the square root of 4 gamma squared minus 2/3 gamma beta plus 1/4 beta squared. So now we have all our distinct solutions. They're all split. So if we now look at all the solutions together, we note that these solutions for the intermediate field Zeeman effect are completely general solutions, which hold for all values of the magnetic field strength, which we parameterize with beta. The 4 solutions, which were already eigenfunctions, start at 2 energies and vary linearly with beta. Remember, you had to negate it, so you start with minus 5 gamma. That's one starting point energy, and minus gamma is the other starting point energy. Minus 5 gamma and gamma. The ones at minus 5 gamma will rise and drop with the slope of beta. And you can see that here. And the ones that start at minus gamma will rise and drop with a slope of 2 beta, as you can see here. The 2 solutions from the first block appear linear at small values of beta. They actually start at the same 2 values, that is, they start at minus gamma and minus 5 gamma, This one starts at minus gamma. This one starts at minus 5 gamma. Has a linear term where beta is small. And then additional terms that look like square roots out here. The third term, the second block, has the same starting points, minus 5 gamma and minus gamma, and again has a linear term and a nonlinear term as you go further out in energy. You'll notice that the red ones have a positive slope initially and eventually, and then the blue ones have always a negative slope going down.